Who cares about infinitesimals? Well, in the previous videos, we considered an infinitesimal rectangular loop in two-dimensional space and established that the flux density across that loop is equal to the divergence of the vector field. In the same way, we established that the circulation density is equal to the curl. But what am I going to do with this information? Where do we actually see such an infinitesimal? And if this is giving you stress, do visit www.dsigma.in and you can get your mind sorted. But before we get to do that, I'm going to share with you how we can apply what we have learned so far to a finite region of space. And in the process, we're going to discover what is called Gauss's theorem, either the fundamental theorem of divergence, and Stokes' theorem, which we can also refer to as the fundamental theorem of curls. Let's get to that. Suppose now that we are considering a finite region of space. So again, we'll restrict our attention to two-dimensional space for now. So let's say we have the two-dimensional coordinate system, the xy axis. And now in this case, we have a finite region of space. And perhaps we are traversing the boundary of that region along the direction which is indicated by the arrow. Now, if you recall a bit of single variable calculus, the essence or the heart of single variable calculus lies in breaking down something large into tiny, tiny parts. So for instance, a directed path or a curve is broken down into tiny little line segments, which we call the tangents. And then as we patch them all together, we end up constructing the curve. Now, in the same way, let's say we have some arbitrary closed loop. What we can do is we can break it down into tiny little grids like this, perhaps. And then ask ourselves the question, what is it that we can infer about the whole finite region of space from what we've figured out so far from the tiny little infinitesimal rectangular loops? So let's do this exercise. Let me pinpoint perhaps one such region, or maybe I'll take two such regions, two neighboring regions, and zoom into that for you. And then let's see if we can reason our way out of it. All right. So I have one rectangular loop, perhaps like this one. That's maybe this top rectangular loop. And then we have the one that's below it, like right here. Now I'm going to put a link to the previous videos where we derived the divergence across such an infinitesimal loop and the curl. And we related that to the flux and what we defined as the circulation. And in order to do that, we looked at directed sort of path, a directed way of traversing this closed loop. And that gave us the directions of tangent and normal vectors, based on which we were able to figure out that the net flux density across the loop is equal to the divergence, and the net circulation is equal to the curl, or rather the circulation density is equal to the curl. So let's say we know the direction in which we are traversing the outer loop, the main region, the main curve that's enclosing the region we're interested in. And for each of these tiny segments, let's traverse the tiny segments along the same direction. So if this is, say, anti-clockwise, I'm going to move in an anti-clockwise direction for the bottom loop, right? So we're going to move like this, this, and this, right? So that's an anti-clockwise movement along the one of these infinitesimal rectangular loops, which constitutes this entire region of finite region of space that we're looking at. Now, in the same way, I'm going to look at the upper loop and perhaps use a different color and see how we're going to traverse that loop. Again, it'll be in the counterclockwise direction. So I'm going to traverse the loop in this manner. So I'm going to move like this, then like this, then like this, and then like this. Now, notice what's happening to this common segment. So this is the common segment which is common to both the loops. What do you think will happen to the, let's say, the flux of a velocity vector or some vector field which you've defined in space? What will happen to the flux contribution across this common segment if I were to sort of sum up the net flux across all of these infinitesimal rectangular loops, right? So for example, let's say the vector field we're interested in looks like this. So it might be going like this, like this, like this, like this, and in this region like this, like this, like this. Now we have this common line segment, right, which is being shared by both these rectangular loops. So I'm going to now just focus on that common line segment. So we have this common line segment AB, right, like this. Okay. We have the vector field, which is perhaps going like this. Now, if I were to take the normal component of this vector field, right, let's say I'm traversing the bottom loop first. I'm going to label that as 1 and then the top loop as 2. So let's say I'm going to traverse the bottom loop first, and we know the vector field is like this. So again, I'm going to use the same notation. So it's Pi plus Qj. Now, as I move toward the bottom loop, the direction of my movement, the direction of the tangent vector is going like this, right? Because we're traversing it in the counterclockwise direction. So what will happen? So the normal to the segment, if I were to calculate the flux of this vector field across this particular segment, the normal to the segment would point outwards, would point in this direction, right? That will be the normal. So if I take the dot product of this vector field, if I take the projection along this, that will also point in this direction, right? So that makes sense, and that's one contribution. But now, when I'm going to traverse the upper loop, which is this part, I'm again going to traverse the same line segment AB. This is the same line segment AB, but this time I'm going to traverse it in the opposite direction, right? So I'm going to traverse it. Let's use the same color. So I used green color. I'm going to traverse it in this manner. But the vector field remains the same, right? The vector field was, or rather the representative vector field was defined at the midpoint of the segment. So I'm just going to draw that again. So the vector field looks like this. Now, if I'm now going to calculate the flux, okay, across this segment for the vector field, which is the same vector field, like Pi plus Qj, the flux would be the component projection of this along the normal to line segment AB, but the normal now would point in the direction which is opposite to the way the normal was defined for the bottom loop, right? Because it has to point to our right. So if I was walking along this loop, the normal, and maybe I should use the same color again, the normal here would now point in this direction, right? So if I take the projection of this vector field along something which is opposite to the one that was defined above, and if I sum up the total flux contribution from both of these rectangular loops, from traversing both of these rectangular loops, I'll find that the total flux across such common segments would just be 0. And that is a very, very powerful feature which will allow us to sum up the flux contribution across all of these tiny little segments to calculate the total flux across this finite region of space and relate it with the divergence of the vector field from the boundaries points of this region. So I'm going to continue this discussion in the next part of the video, but just give it a thought of what we are doing. And also, as a quick exercise, what we just did was showed you that the flux components across the common line segments which are being shared by the rectangular loops, cancel out. Try as a quick exercise to see what happens to the components of the vector field along the tangents, which is what we use to define the circulation. So what happens to the tangential components of the vector fields? Do they also cancel out? Hope to catch you soon again. Thanks for watching.